So I'm reminded right now that I'm in the singular position of having an advantage over you, is that I'm allowed to drink up here. They've got water up here. So, okay, what am I talking about today? The minimum circuit size problem, which I will always abbreviate MCSP. What is the problem? You get as input a bit string, which I would normally call X, but I'm going to call it F because it's the truth table of a Boolean function. So that it's a bit string of length 2 to the k for some k, and a number I. And you want to know if F has a circuit of size less than or equal to I. The problem has an extremely long history, going back actually to the 1950s, which certainly predates most work in computational complexity theory. This was studied fairly intensively in Moscow because already there, before computational complexity theory was really formalized, there was intense interest in what were the class of problems where there were no clever solutions, where you really had to just brute force search your way through some search space. And I don't speak Russian, but in the literature that's been translated that describes this, they always use the word perabor, which was the Russian notion, which problems really require perabor, require brute force search. And Yablonsky, who was extremely influential in the Moscow mathematical community and in fact rose to a level of, I would say, dominance, certainly political dominance in determining who had money, who had ability to travel, et cetera. A lot of people really felt they were under the thumb of Yablonsky. Again, this is all secondhand. I know nothing. But he proved a result that to him and his students meant that the only way to figure out if a circuit, if a truth table had a small circuit was to basically try them all, to perabor, brute force search your way through the entire problem. And of course, if this had held up to modern standards of what it means to have to do a brute force search, this would prove that P is different from NP, because this problem is certainly in NP. Why is this? Well, you've got the entire truth table, and a DNF or CNF expression for this is certainly exponential in the number of variables, which is linear in the size of the truth table. And so you can just, I is meaningless if I is much bigger than the size of F. And so you can just guess the small circuit, and you've got time to check all of the, check to make sure that the circuit computes correctly each bit of the truth table. And so it's easily in NP. And if this really did require perabor, if it required searching through all the circuits, well, then we would know that P is different from NP. And in fact, Leonid Levin once told me that he delayed publication of his work, essentially along with Cook, defining and highlighting the importance of the class NP and proving that SAT is NP complete, because he didn't care that much about satisfiability. He wanted to nail the complexity of this problem, because Yablonsky was the one who was making life sort of miserable for a lot of people, including perhaps Leonid to some extent, and he didn't buy. Basically what Jablonski had shown was that a certain restricted class of algorithms would not work to solve MCSP quickly. So he really wanted to nail the complexity of this problem. And now it's, 40 years later, 50 maybe, I forget. We still don't know what the complexity of this problem is. And that's what I'm going to talk about. What have we learned about the complexity of this problem? And in the title I gave here, this is, after all, on parameterized complexity. There's a parameter. And this problem really has not been studied that much in the context of parameterized complexity, although there are a number of papers that do mention what they call the parameterized minimum circuit size problem. But the parameters that come up there are typically when I is nearly as big as is meaningful. Or you fix a fairly large value for I. And the question, what happens when I is fixed to a fairly small value? We really don't know much about the complexity there. So that's your homework for those of you who, unlike me, really work in the area of parameterized complexity to try to say more. But there's still a lot that we can talk about. And so let's get started. I've mentioned the early history, the prehistory, dating back to the 1950s. And then this problem sort of languished, largely because nobody knew what to do about it. It's hard to say what, you don't publish anything unless you've got something interesting to say. And then there was this very important, influential paper by Razborov and Rudich on natural proofs. And I don't want to bore everybody here. Raise your hand if you are already really familiar with the natural proofs framework and you don't need me to remind you what that is. Okay, hardly anybody. So let me tell you what was going on. The context for their work is starting in the 1980s. Circuit complexity started to have a rebirth, a renaissance. People studied very small subclasses of NP, or small subclasses of P, defined in terms of very restricted classes of circuits. And I will present soon. In fact, why don't I go ahead and present some of these complexity classes now. Here's NP. Well, inside it, we have P. We're going to need to talk about non-deterministic log space at some point. Do I need to define what non-deterministic log space is? Deterministic log space. Now we're going to go into what might be less familiar territory for people. AC0 is what you can do with constant depth circuits of unbounded fan-in and unbounded fan-in OR gates, and of course negations also. So everybody knows what disjunctive and conjunctive normal form are. Those correspond to depth 2 circuits, right? A disjunctive normal form is an OR of a bunch of ANDs, where each AND is connected to a variable xi or a negated variable xj, etc. So depth is the length of the longest path from the input to the output gate. Constant depth circuits of ands and ors, and polynomial size. Size here being, let's say, the number of gates or the number of wires. These are going to be polynomially related. It doesn't really make any difference. Okay, so just a slight generalization of what you can do with small conjunctive normal form or disjunctive normal form formulae. And influential work by Sipser, first Saxon Sipser, Aitai, and then Hostad and Yao and various others proved various very simple problems require exponential size AC0 circuits. And that was exciting. One of those problems was the parity problem, which is just taking n bits and when you find out if an odd or even number of them are on. So parity is not in AC0. What happens next? Well, you can take AC0 and augment it with parity gates. So it's constant depth circuits with and or not and parity gates. And brilliant, lovely work showed that exponential size was required to do the mod 3 function. Okay, what's next? Well, you take any prime modulus. In other words, is the number of inputs that are on a multiple of p. That cannot be done, mod q cannot be done with mod p AC0 circuits if q does not divide p. Okay, all of this rapid progress, and then decades of no further progress. And this was the context where Rezborov and Rudich stepped in to say, what's going on? Why are we stuck at this ridiculously low level? We can only deal with prime moduli. We can't even talk about mod 6 gates. Is that really more powerful? And what Rezborov and Rudich did was they analyzed the way people were proving circuit lower bounds. And, well, think about it. How would you try to prove a circuit lower bound? You identify, or a common thread of a lot of proofs was to identify a property, let's call it Q, that is useful against some circuit class C, and I'm going to parameterize it by S. In other words, this is C circuits of size S. What does this mean? You think about what you can do with small circuits of a particular type, and it seems like, these circuits really can't do something. They can't compute functions that have a particular property. Okay, so a property is a property that functions have, certain functions, but no function that's got small circuits has. So F is in Q means F is not of circuits of size S. So in other words, what is Q? It's a property. It's a set of truth tables, basically. And if you're formulating a lower bound proof, and you've got some property that you're trying to isolate, typically it's going to be something that you're able to actually think about and reason about. So in particular, the set of F such that F has property Q should be easy. Easy to compute in some sense, maybe in P. In other words, it should be able to recognize, given the entire truth table, does the function have that property? Or maybe having it be in P is even too restrictive. There's another class I'm going to introduce later, but for right now, just think of, we'll use the usual notion of easy. And what's the other property? What's the usual way you get your hands on a hard function? Well, you just pick one at random, right? Hardly any, this is the standard observation that goes back to Shannon. You just pick a function at random, it's not going to have small circuits. So most F should have property Q. And if you have a lower bound proof that identifies a particular property and a function that has this property, where the property is useful against small circuits, and a random function is going to have this property also, that's the structure of what they called a natural proof. What does this have to do with the minimum circuit size problem? Well, this set, if it were easy to recognize, if it were in P, would give rise to sort of a canonical example of a natural property, right? Because most things require big circuits, and if you set, if you look at the complement of this set, the set of all F that require, does not have circuits of a particular size, then that will be useful against small circuits. So this is the canonical example of a natural proof property, except that it doesn't seem to be easy to compute. And what did Razborov and Rudich show? Natural proofs useful against, let's introduce this class now, P poly, which is functions with circuits of size polynomial in the number of inputs. Natural proofs useful against P poly imply there do not exist cryptographically secure one-way functions. So, after Razborov and Rudich did this, Cabinets and Tsai observed that, of course, the minimum circuit size problem is this canonical example of a natural proof, which is to say that if this were in P, or even if it were in P poly, then there would be no cryptographically secure one-way functions, which is fairly strong evidence that this is a hard problem. Okay, so that's the beginning of modern history, except that I haven't explained how this connection proceeds. I will do that later today or next time. Okay, so that's why people think it's not in P. The obvious other thing to ask is, well, why don't people just try to show it's NP complete and be done with it? Because that's the usual thing we do. In this same paper by Kabinets and Tsai, they asked that question also. And they showed that if MCSP is NP complete, under, again, this ugly word natural appears, natural polynomial time M reductions. That implies, well, we know more now, but at that time, BPP is in the intersection epsilon greater than 0, deterministic time 2 to the n to the epsilon. In other words, if it were NP complete under the usual types of reductions, then we'd have this really lovely upper bound on a complexity class that some of you probably don't know what it is. So I need to introduce more complexity classes. We've got P, we've got NP. Another important complexity class is what you can do with probabilistic polynomial time. And there are at least 3 definitions of what probabilistic polynomial time ought to be. There's RP, which is just like NP, except if there are any accepting computations, there are a whole lot of them. So that if you just flip a random coin flip sequence of n to the k bits, it will give you the right answer. Either there are no accepting computation paths, or the overwhelming majority of the computation paths are correct. And just as there's NP and co-NP, so there is co-RP. And the intersection of RP and co-RP is called ZPP. ZPP stands for zero error probabilistic polynomial time. Why is it called zero error? If you've got an algorithm such that on all the yes instances, a random coin flip sequence will give you a proof that it's a yes instance, and a different algorithm such that on all the no instances, a random coin flip sequence will give you a proof that it's a no instance, then on every instance, if you just try a bunch of random coin flip sequences, very soon you're going to get a proof that it's either a yes or a no instance if you just run these in parallel. And so in expected polynomial time, you will get the correct answer with probability 1, which means it's a zero error probabilistic polynomial time. And above all of those is BPP, which is the class of, it's the usual way you would try to define probabilistic polynomial time. On input X, you flip a bunch of coins, and you run your polynomial time algorithm. You're going to get the right answer with 99% probability. There's a small chance of error on the yes instances, a small chance of error on the no instances. We don't know that BPP is contained in NP or in co-NP. It is contained in the second level of the hierarchy, which doesn't fit on the board right now. But even down here, the best upper bound we have deterministically is exponential time. And so when Cabinets and Tsai proved this, it means that if you could prove something is NP complete using the type of reduction that you will find if you open up Gary and Johnson to a random page, you'll get a very, a lovely low complexity simulation deterministically of that probabilistic algorithm, which means that you're probably not going to have any luck finding an ordinary NP completeness proof. Question?
Yeah, so is it obvious that RP and co-RP live inside BPP?
Yes. So RP, so on input x, if x is in A, the probability of that m on input x equals 1 is greater than or equal to 99%. And if x is not in A, the probability that m of x equals 1 is equal to 0. This is the definition of RP. You've got an algorithm for A like this. And for BPP, you are allowing this to be less than or equal to 1%. And 0 is certainly. So it's just a weakening. And 99% and 1% are arbitrary. In fact, you can make these exponentially small. Yeah. Well, that's the next thing I was going to mention. Thank you very much.
So that's not very strong evidence.
That's right. It stinks. Okay. So let me fill people up in a little bit more. What we know is that ZPP is contained in exponential time, and that's the best thing we know. But there is this beautiful result, which I will state more formally later by Impagliazzo and Vigderson, that says if exponential time is not contained in what you can do with circuits of size 2 to the epsilon n for some epsilon greater than 0, that implies that BPP is equal to P. E is deterministic time 2 to the order n. Lots of stuff that we think is very hard lives here. Satisfiability. Your favorite NP-complete problems are not only in NP, they're in non-deterministic linear time. They're also going to be in E. Anything in linear space, which seems to be a lot more complicated, is also in E. Things in E actually require exponential time. Duh. That's why it's, the diagonalization says there's a lot of stuff there that really requires exponential time. So it's inconceivable to many of us who have limited imaginations, it's inconceivable that exponential time doesn't actually require exponential size circuits. Things in exponential space require exponential size circuits. It's just pushing things down. This is a very plausible hypothesis. And under this hypothesis, anything you can do efficiently with a probabilistic algorithm, you can do nearly as efficiently with a deterministic algorithm, which means that not only do we think BPP has sub-exponential time algorithms, it collapses all the way to P, which means that this is not evidence that this is false. It's just evidence that you're not going to be able to find a proof anytime soon. And in fact, this is a recurring theme in work on the minimum circuit size problem. We will see a lot of results of the form, basically of the form false implies true. Something that we think is probably not true implies something that we think is probably true, but we don't know how to prove it. Which is not a very comfortable situation to be in, but there are some results that actually do give stronger evidence against MCSP being NP-complete, if you're willing to accept flimsy evidence. So this is why I'm giving this talk. This is an area where we need more work. And we actually have found some stuff out. Okay? Feel free to ask more questions. I've skipped over some stuff I wanted to say, so let's talk about some of that other stuff. Going all the way back to Russia or the Soviet Union in the 1950s. There was a lot of other stuff happening in Moscow. Kolmogorov was there, and he had interest in what's now known as Kolmogorov complexity. And these people talked to each other, and people certainly realized that there was some vague connection between MCSP and some version of time-bounded Kolmogorov complexity. And why is this? Here's F. It's an exponentially big string. It's got length 2 to the k. Let's say that F has a small circuit C. Well, this circuit is a very short description of the truth table of F. Not only that, but if you want to get your hands on the ith bit of F, you just feed I into this circuit, and that gives you the ith bit. And you can compute that very quickly. So there's obviously some sort of connection. If something has a small circuit, it's got small time-bounded Kolmogorov complexity in some sense. This audience probably knows a lot about Kolmogorov complexity, and you've seen time-bounded Kolmogorov complexity. And I don't know if all of you really appreciate how bad some of those definitions of time-bounded Kolmogorov complexity are. What is it that makes Kolmogorov complexity useful? It's the fact that you can have a universal Turing machine, and Cu of x is less than or equal to Cu prime of x plus or minus a constant. In other words, there's this completely arbitrary choice. You pick one universal machine and you say, that's the one we're going to use, and it doesn't make any difference because we don't care about the constants. And if it weren't for that, the whole theory would be useless. And so what do people do with time-bounded Kolmogorov complexity? Well, the usual standard definition is to say Ct of x is the minimum length of a description such that our universal machine, here for universal machine, u d equals x in time less than or equal to t. Oh, let's change the universal machine. What does that do to this complexity? It shoots it all to hell. You know, the usual way people get around this is they say, well, if you change the machine, you can change the running time a little bit, and it's not too bad. And for a lot of applications, that's just fine. But it certainly isn't nearly as clean a definition. And partly for this reason, and partly for completely different reasons, Levin defined a definition that he called kt of x, which takes advantage or takes account of time in a different way. Namely, it's the minimum. We're not going to pick the minimum length of a description anymore, although that's going to be part of it. Minimum length of a description plus log of the running time, such that the universal machine D outputs x in less than or equal to t steps. Anybody notice anything funny about this definition? What's the first thing you look at, you ask when you see this definition? Why log? What's so special about log of the running time? Well, Levin had a really good reason for doing this. Namely, this is something that's actually done as an exercise in a lot of complexity books, but it gets buried someplace sometimes. I don't know if everybody knows this. For 40 years or so, we have actually known an asymptotically optimal algorithm defined satisfying assignments for satisfiable Boolean formulae. You know, so we know what this optimal. Raise your hand if you've already seen this, so I won't bore people. People don't know this. Okay. So if all we need to do is just analyze the running time of this particular algorithm. You know, so what is that algorithm? On input, given a formula phi, for, let's say, m equals 1 to the length of phi, or let's just say formula phi has n variables. So for m equals 1 to n, for all descriptions d of length m, run u on d for m steps, and if this outputs or let's just say run u of d for m steps and let the output be z. If phi of z equals 1, output z. End for. This is basically just searching through strings of length n in order of increasing kt complexity. You know, you look for all the strings of kt complexity 1, all the strings of kt complexity 2, which means you're looking at all the short descriptions and running them. This should be for 2 to the m steps. So, you know, you'll stop after m is equal to n. You know, you'll go up to you'll be running exponential time if you ever get through the end there. But if there is any algorithm at all that finds satisfiable assignments in time t, then this algorithm finds satisfying assignments in time something like t cubed. And why is that? Well, if you've got an algorithm that finds satisfying assignments quickly, what is it doing? Oh, I should be running U on input D and phi. So we're actually looking at relative KT complexity. If you've got a fast algorithm that finds satisfying assignments, what's it doing? Given a formula, let that program just be a constant number of bits, run it quickly, and so the output has got small KT complexity relative to phi. So this algorithm is asymptotically optimal, but it's completely worthless in practice because if there's this big O in the running time. So let's say that your optimal algorithm for finding satisfiable assignments has got program of size 500, then the running time here is going to be 2 to the 500 times the running time of that algorithm cubed. Okay, so the constant factor overhead makes this completely useless in practice, which is why nobody ever actually, I shouldn't say that. Some people really do try to study the complexity of this approach, and they've got some systems that work reasonably. But this trying to understand the running time of this algorithm does not seem to be the way to understand the complexity of satisfiability. But for this discussion, the point is that's why Levin used log in the running time, is because if you're trying to find the fastest approach to search through a big search space that's related to NP, this is the optimal search order that you want to use. Am I making my point, or is that, have I just lost everybody? People want me to move on or try to elaborate on this? Because what's relevant to our discussion here is that this complexity, KT of function f, if f is the bit string relating, the bit string of a function, is roughly, polynomially related to the circuit size of f, almost. It's not on ordinary circuits. This is on circuits that have fan-into AND gates, fan-into OR gates, NOT gates, and oracle gates, where the oracle comes from exponential time. What's an oracle gate? If you've got some language, A, and you feed Z into it, it outputs 1 or 0 according to if Z is in A or if Z is not in A. So it's just a piece of hardware that takes K input bits and answers this question about an oracle. So when you see an equivalence like this, it makes you scream, but I don't care about oracle gates. I really care about ordinary circuits without the oracle gates. Actually, that's not true. I really do care about the oracle gates. But let's pretend that I really don't, and that I want to talk about circuits without oracle gates. Then this definition doesn't work. And the reason it doesn't work is because of the precise reason that Levin's definition was right, namely it's because the log of the running time. But if we do the obvious thing and replace log with just t, well, what do you know? Every string x, if x has length n, it's going to take you at least time n to output the string, and so everything is going to have linear complexity, which means everything's random and it's not very interesting. So we need to fix this definition in order to make it useful. Well, let's just do that. Let's, in fact, go back to ordinary Kolmogorov complexity. No time bound. The complexity of x is the length of the minimum description. But we could have changed this definition as follows. The complexity of x is the minimum length of the description such that u, given the description d, and the number I, gives you the ith bit for 1 less than or equal to I less than or equal to length x. And if you want to know what the length of x is, then you can actually go up to more than the length of x, so that x sub n plus 1 is out of bounds, just so you can figure out what the length of the string is. This definition is identical to the usual definition. Plus or minus a constant, but plus or minus a constant doesn't make any difference. Namely, a short description is a short description if it tells you the length of the string and it tells you what every bit is. Similarly, Levin's definition can be changed in the same way, and it doesn't really make any difference. Oh, I should mention, if you change the universal machine, it just doesn't, it's no longer a constant difference, but it's just a logarithmic additive term, and we don't care about that. Question?
But shouldn't you have like a slash, relative to the length? Let's see how you get the length.
Because what is, if I is the length of x plus 1, what is ud of xi? Well, it's not 0 and it's not 1.
Okay, so it's already undetermined. Okay.
So if we modify ordinary Kolmogorov complexity and modify Levin's definition and get rid of the log, we get a new definition, which is k capital T, and k capital T of f is roughly the same thing as ordinary circuit size, and that, I think, is reasonable justification for codifying this as a definition. Because we care about circuit size, we care about Kolmogorov complexity, and this is a reasonable approximation of circuit size and Kolmogorov complexity. And the standard definition doesn't really have that property. In other words, the one where we just fix the time bound up there. So it's got a number of nice properties. And you can say, yeah, but we don't really care about this. But I didn't really emphasize before, what's the size of a circuit? Well, it's the number of gates, or the number of wires, or maybe the number of bits that you use to describe the circuit in some standard formalism. All of those choices give rise to a different problem. And also, what types of gates are you using? Unbounded fan-in? Fan-in 2? Do you allow parity gates? You've got a lot of choices. Each choice gives you a different problem. And you could say, yeah, but you could look at satisfiability and write the formula in Roman script or in italics, and they're different problems, but they're really all the same. Yeah, but with satisfiability, you can introduce them. Here, all of these different choices give you problems that we don't know how to reduce one to the other. Similarly, change the universal machine, it doesn't change the complexity by very much, but if you look at MKTP, just replacing circuit size as a complexity measure with KT complexity, which is the set x, comma I, such that KT of x less than or equal to I. If you change the universal machine, you get a different problem. We don't know how to reduce these problems to each other. On the other hand, you can say, but it really shouldn't make much difference, and that at least is true. Anything that we can prove for one, for MKTP using one universal machine, we can prove for any of the other variants. And until very recently, anything we could prove for MCSP using any of the size variants also carried over to MKTP. So it was basically studied just as another variant of MCSP. But recently, there have been some things that we know how to prove for this problem that are still not known here. For instance, I've spent way much more time than I thought I would take to get to this point. We know that MKTP is not in AC0 mod 2. This is the non-uniform version, meaning we don't care, this problem on inputs of size n requires very large circuits of constant depth with parity gates, even if we don't additionally require that we be able to build those circuits. On the other hand, MCSP we know is not in AC0. This is a theorem, but MCSP we don't know if it's in AC0 mod 2. So this shouldn't be. This is actually very embarrassing that we are in the situation where there's this problem that can't be easy unless there is no crypto. And I haven't gotten as far as I thought I would to tell you what we do know about the complexity of this problem. But even trivial, what should be trivial lower bounds, we still don't know for the minimum circuit size. According to the schedule, I should be done like 5 minutes ago. I could go on for another hour, but I am going to go on for another 2 hours other days anyway, so maybe I'll just stop now. I will be mentioning that. Actually, graph isomorphism will play a big role in the forthcoming lectures. We know that graph isomorphism is in RP relative to MCSP, and graph automorphism is in ZPP relative to MKTP. Well, it's actually in RP relative to MKTP also. So this was actually the first place where weird stuff started to happen. We could prove better upper bounds using MKTP than we could using MCSP. And in fact, I should really make a connection to Alan's talk before everybody forgets about this. There's an important class called statistical zero knowledge. Zero knowledge interactive proofs, big topic in cryptography theory, complexity theory, and it really all began with an observation about graph isomorphism. And I'll remind people about this next lecture, namely that graph isomorphism has got a zero knowledge interactive proof, and I'll tell you what that is. Zero knowledge interactive proofs are in NP/poly intersect co-NP/poly. I'll remind you what the /poly stuff means, but think of this as meaning almost in NP intersect co-NP. And the thing about zero knowledge, well, here's a fact. Statistical zero knowledge is in BPP relative to MCSP, and this also holds for MKTP. So a lot of crypto stuff is here. In fact, most crypto problems reside here. So we think there's a lot of hard problems in here, and they're all reducible to MCSP. This has complete problems. But they are promise problems. And Alan mentioned promise problems very briefly. What's a promise problem? Well, like any computational problems, you have yes instances and no instances. Typically, that's all there is. You know, you've got an input, you want to know, should we say yes or should we say no? But for a promise problem, there can be other things, these so-called don't care problems. What's the connection to Alan's talk? These are disjoint sets, obviously. And a solution is anything that says yes to all the yes instances and doesn't say, and says no to all the no instances. And the study of SZK was a mess until people realized that it's got fairly natural and important complete problems, and you can't formalize this unless you do it in the promise problem framework. And so they, you know, even if you didn't like promise problems, you'd be dragged kicking and screaming to embrace the notion, because it's the only way you can really make sense of this complexity class.